Alright guys, so today we begin a new chapter in this video. So we move on through the chapters now, doing the continuous probability distribution. So as opposed to the previous chapter in which we cover the discrete probability distributions, in this case we cover the cases in which we are dealing with continuous random variables. And let's recall the definition of a continuous random variable in which it takes infinitely many values. Remember the examples we have been talking about, the number of x from a hen, and that's a discrete random variable. That's one egg. 2x, there's no such thing as half an egg. Or the number of times we roll a die. We roll it once, twice, 3 times, etc., but we don't roll it 1.5 times. In this case, we are going to look at a different case in which we rely on continuous random variables. We begin with the normal distribution. So, you might remember this bell curve. We looked at it on chapter 3 when we covered z-scores. And we briefly discussed about the distribution data when we have the mean exactly in the middle of the distribution. Well, we can conclude that the data is normally distributed. So in this case, how are we going to calculate the probability when we have a normal distribution? So it will be the equivalent of finding the area under the curve. Under which curve? Well, this bell curve that we have here, it's given by this function y equals e to the negative x minus mu squared divided by 2 sigma squared, the whole thing divided by sigma times the square root of 2 pi. Well, that looks kind of big. Okay, that looks kind of big. And let's describe the parameters. So the parameters are sigma, which is the standard deviation, and mu, which is the mean of the data. Okay, so again, in this case, let's keep in mind that this graph goes on forever and ever and ever, as we discussed earlier in chapter 3. So we are going to find all the area from negative infinity to positive infinity. So the probability distribution p of x will be the integral from negative infinity to positive infinity of whatever probability function f of x. Okay, so in this case, this f of x happens to be this ugly looking function, which I will highlight. Okay, the problem here is, number one, not all of you have taken a calculus class to do this the integration way. And number two, even if you took at least a calculus class, calc 2 class, where we cover methods of integration, we would have to integrate e to the negative x squared, which in this case it's not possible. We would need a different tool called the gamma function. But the gamma function is a function introduced in a higher level of math, in engineering and science math, which is not part of our course. So in this case, we're going to find the probability using way easier method. So if we were in the classroom, I will be showing you how to use table A2 to calculate those probabilities. However, I'm just going to be limiting to show you how to do it on the graphing calculator. Okay, so let's look at the characteristics of the normal distribution. So number one, the distribution is symmetrical around the mean, as we saw on the bell-shaped curve. The mean and the median and the mode are exactly the same value. That's why, as we discussed in chapter 7, they are the same in the three. The three of them are in the very middle. And finally, the total area under the curve is equal to 1. Let me go back here to the picture. So if we find this area under the curve, this area from negative infinity to positive infinity would be 1. Okay, and again, that let's make a connection with the discrete probability distributions. Remember, from random variables, the sum of all the probabilities are equal to 1, and all individual probabilities are between 0 and 1. Okay, so if we add them together, we get the 1. So the parameters for the normal probability distribution, number 1, the mean, which is the center of the normal distribution. Okay, and the standard deviation. So you might remember these two parameters when we cover the empirical rule, and we have some trouble with the empirical rule when we didn't know exactly somewhere in between standard deviations. In this case, we will be able to do all to find the probability for every single random variable. And in this case, the z-score. So for the z-score part, I'm going to skip it because we're not doing the table way. I'm just going to show you how to do it on the graphing calculator. I will give you the table though in the future, and if we have time at the end of the semester, I will show you how to do it on the graphing calculator. Okay, I mean using the table. Okay, so let's look at an example to show you how these probability distributions work. So car passed through a checkpoint. Okay, and if we assume that the speeds are normally distributed in a way that the mean velocity, the mean speed of all cars is 61 miles per hour, and with some standard deviation of 4 miles per hour. Okay, so they're asking us to find the probability that the next car that passes through the checkpoint will be traveling slower than 65 miles per hour. Okay, so first of all, we are going to label our given information, which is going to be exactly in the middle right here. So here, the mean will be 61 and the standard deviation will be 4. Okay, so they're asking us to go and find the probability that a car is slower than 65. So I'm just going to label this 65 with green because it's larger than 61. So in this case, this will be our random variable x equals 65. And in this case, I'm going to shade the region on this bell curve corresponding to less than 65, because in this case, they're asking us for slower than 65. So I'm going to shade below the curve, and I'm going to find the area under that curve. That area under the curve would be the probability. That'll be the probability that we're looking for. However, again, like I mentioned before, I'm not going to ask you to do the integral because we don't have all the necessary tools to evaluate such an integral. So in this case, what are we going to do? We're going to go to our graphing calculator. I'm going to show you the parameters. So P of x less than 65, we will use the function Normalcdf of lower. Okay, I'm going to write down lower below, upper, mean, and standard deviation. Those are going to be the 4 parameters of this distribution. Okay, so in this case, notice we are shading below the 65. So this shading as I'm doing here, it's going to extend all the way to negative infinity. So in this case, to ensure that we are correctly calculating this probability, put for the lower endpoint a very small number. I typically just type negative 9999, a huge number, a negative huge number, and then the upper, so negative huge, and then the upper limit, which is 65, and then the mean, which is 61, and the standard deviation, which is 4. Let me show you how to do this in the graphing calculator. So let's do, we're gonna go second dist, and in this case, notice we have two normals. We're not going to use normal PDF. I'm going to use normal CDF. Normal CDF, and then I'm going to click enter. So the lower, which in fact is giving us a way bigger number. So by default, it's given. I'm going to go to the upper, which is 65, and the mean, which is 61, and the standard deviation, which is 4. Then I'm going to click paste. All right, and I'm going to get 0.8413. In this case, I'm going to round to 4 decimal places. Depending on the case, it might be the case in which we round up to 3, sometimes to 4. So let me go back to this, and that is the probability, 0.8413. How do we know this makes sense? Well, that's basically 84%. Look at the portion of the graph that we shaded. It's kind of big. It looks like it represents 84% of it. Okay, let's calculate the probability. Sorry about that. The probability that the next car will be traveling more than 65 miles per hour. Okay, so let me label the mean, which is 65. No, not 65, it's actually 61. And the standard deviation, which is 4. And then in this case, I'm going to go not 65, but rather 66, which is a little bit higher than 61. And I'm going to do the same. I'm going to find the probability. Okay, but in this case, notice we are traveling more than 65 miles per hour. More than. This more than we are going to shade to the right of the lower limit. And then notice this is going to extend all the way to infinity. So let's see. So this is now going to be a positive, huge number. So P of X greater than 66 this time. This is going to be normal CDF of lower, which in this case is 66, upper, which in this case just put a big number, I don't know, 9999. So how big? In a way that is impossibly big relatively to the situation that we have. So imagine traveling at this speed is huge, it's big. So just to be sure that it's going to cover all the highest endpoint of the graph, and then the mean, which is 61, and for the standard deviation, let me go to the graphing calculator here. So I'm going to use, let me clear all this, let me clear the window, and let me go second dist, normal CDF, enter, and then the lower in this case is 66, and the highest I'm just going to type a bunch of 9s, okay? And then the mean and the standard deviation, because we're working with the same numbers, sometimes in the calculator they will remain the same. Let's just paste and click enter. So what do we get? 0.1056. So 0.1056 is the probability. That's basically 11%, which, look at the portion of the graph that is shaded. Why not 11%? Okay, so the probability that the next car will be traveling 59 miles per hour, I will leave it to you. Use the calculator. You should be obtaining, so x less than 59. This will be 0.3085. That's what I got here. And the next one, I'll leave it to you as well, but I'm gonna jump to the next example to move on through this. Okay, so we have a different situation in which a retail store has customers whose ages are normally distributed, actually. In this case, the mean age is 37.5 years old, with a standard deviation of 7.6 years. Okay, years old. Okay, so let's calculate the probability that a randomly chosen customer is more than 48 years old. Okay, notice 48 years old is somewhere here. Okay, it's bigger than, so x equals 48, and the probability that we get, actually, let's shade the part of the graph, in this case to the right. So p of x greater than 48 will be equal to normal CDF of lower, which is 48, upper, which is, I'm gonna say 9999, all a bunch of nines, big number, and the mean, which is 37.5, and the standard deviation, which is 7.6. Okay, this will be equal to 0.0836 if you use the graphing calculator. Okay, I will skip the showing you how to do the graphing calculator. If you have questions on how to put it, in this case, go back, just rewind the video a couple minutes so you can see the process. Okay, so for the probability that a randomly chosen customer is younger than 44. Okay, so in this case, let's label the same mean, and in this case, mu equals 37.5, sigma standard deviation 7.6. 44 is our random variable. Let's put it over here. And in this case, we are going to shade below. How do we know that we shade below? Well, because the question here is that the customer is younger than 44 years old. So look at how big this is. So it looks like, why not? It looks like it's going to be a big number. So let's put this like p x less than 44. Okay, less than 44, that is normal CDF of, start with a negative huge number like negative 99999, comma, bigger, which is a 44, and then the parameters mu and sigma 37.5 and 7.6. Okay, so if we're using the graphing calculator, you should get 0.8038, which which is basically 80%. If you change this to percent and look at the portion of the graph that is being shaded and represented, looks like 80% of it. All right, for the next one, I'm going to show you how to do it in the calculator. So let's establish the mean, which is 37.5, and sigma, which is 7.6. Okay, and they're asking us between 46 and 54. That is, I don't know, I'm gonna say maybe 46 and 54. So they're asking us for this little portion of area that will represent the probability that a randomly chosen customer is between 46 and 54 years old. Now, how are we going to use this? Well, let's represent this using probability notation P of 46 less than x less than 54. Okay, this will be normal CDF of 46. In this case, we don't have to look for a huge negative or a huge positive because this is going to be the lower and this will be the upper. Okay, lower, upper, and lower. So 46, 54, 37.5, 7.6. And let me show you how to put it in the graphing calculator. Let me clear and clear. Okay, so second dist, normal CDF. Click enter. And now we will put the parameters the same as we have them here. 46, enter, 54. Now we're going to change the mean, which is 37.5, and sigma, which is 7.6. Okay, and paste and click enter again, and then you can see all the buttons that have been pressed for this calculation to be undertaken. So what are we going to have? We have point. Oh, by the way, looks like I did a silly mistake. It wasn't supposed to be 45. It was supposed to be 46. Let me repeat the calculation. So 40, 46, and 54. Okay. Enter. So 1167 is the answer. 1167. I mean, point 1167. Which is basically 12%. So look at the small portion of area that represents 12%, if you will. Why not? It's a very tiny region. Okay, so let's see. Let's look at another example. The probability that a randomly chosen customer is between 25 and 37.5 years old. Okay, let's write down the mean first. The mean will be 37.5 and the standard deviation will be 25. So we're looking for 25 between x equals 25 and x equals actually 37. It's actually x. So we're looking for this portion of area. Okay. Let's see. So let me clear everything. Clear. second dist normal CDF, and in this case 25, 37.5, and the rest of the parameters are there correctly. Just click enter and we get 44.99. That's basically, well, let's just keep it 0.4499. I know this rounds up to basically 0.5000, 0.4499. Okay, so P of 25 less than X less than 37.5. This will be normal CDF. Okay, you know the parameters that we wrote. Well, let me actually write them down. That's 25, 37.5, comma 37.5, comma 7.6. By the way, I made a little mistake here. This should have been 7.6, not 25. And let's, because there's two 37.5s here, let's call this a lower, upper, and the mean and the standard deviation, called sigma. Okay, what did we get here? Again, I believe we got 0.4499. That is basically 45%. Okay. Now we're going to look at a different type of question, find the 43rd percentile. So you might remember these percentiles and quartiles from that chapter 3. So we are going to learn how to do this in the sense of a normal distribution. So in this case, we are going to use a different command. We are going to use the inv-norm, and the commands are going to be the percentile as decimal, comma, the mean, and the standard deviation. Okay, let's see how that works on the graphing calculator. So let me clear. So I'm gonna go second dist, and I'm gonna go to inv-norm, click enter. So area that represents the area that we want, in this case, that's 0.43, because we want the 43rd percentile, the mean, which is 37.5, and the standard deviation, which is 7.6. Okay. All right, the tail, I'm not sure what it is. Okay, let me just call this let me just call it center. Just see what happens. Hopefully it matches my result. Then center, enter, and paste. Okay, let's see, what do I get? Okay, no, it doesn't seem like I got something. Okay, let me do this again, and this is what I'm going to do. I'm going to delete the word center, delete, and delete the comma, and let's see what we get. And I get 36.16. That's the person that is listed in the 36th percentile. Okay, if we were to represent all the ages of the people from the youngest to the oldest, they are normally distributed, okay, with a mean of 37 years old, 37.5 years old, and a standard deviation of 7.6. So the person that would be on the 43rd place would be someone that is 36 years old. That's what we mean. Okay, so let me go back to the document. I get 36. So inv-norm, of 0.43, 37.5, 7.6. Okay, and we get 36.16 years old. You might want to omit the 0.16. It's not very meaningful when we talk about age. So I mean, throughout the entire year, a person is 36 years old. We don't say, oh, I'm 36.5 years old. We just say, I'm 36 years old. Find the 87th percentile. Okay, I'll leave this up to you. I'm going to write the operation in the norm. In the norm of 0.87, 37.5, 7.6, and choose left, right, and center, whatever you want, and be sure to delete those two commands that send that whatever you choose and that comma. Be sure on the graphing calculator it reads like this, and in this case you should get 46.06 years old. But again, you might want to just say 46 years old. Okay, and that's the normal distribution. So let's move on to another distribution, the uniform distribution. In this case, you might remember, let me go back to what we learned back in those distributions. When we went over how data is distributed, we got it skewed to the right, skewed to the left, normal, or simply uniformly distributed. Okay, so it is always the same probability, whatever, for every single random variable. Okay, so in this case we are going to have two values that we know are the endpoints, the minimum and the maximum of distribution of data. And all intervals should be the same between those values A and B. Okay, and they have equal probability. Again, going back to this mini graph. So if we draw uniform distribution, the probability for x equals 1, for example, let's say 1/4. The probability for x equals 2, also 1/4, etc. Whatever x you choose will have the same probability of happening. Okay, so what are we going to do in this case? To calculate the probability that a random variable will lie between some x1 and x2 in the distribution, we use the given formula right here. In this case, B and A will be given, and x2 and x1 will be part of the question. Okay, so we have a vending machine that dispenses coffee in amounts that vary uniformly between 7.4 and 8.2 ounces per cup, right? So for example, you go to AM/PM, you go to those coffee machines or those soda machines that dispense drinks. Those machines are already programmed. You press the button and it serves or at McDonald's, they press the button to fill a medium drink. Or if it's a large cup, they press a different button and it dispenses a different volume. But those machines are never perfect. It goes plus minus some milliliters of drink, and in this case, we end up having a range of values. So in this case, those amounts of coffee in this case vary between 7.4 and 8.2 ounces. So we are going to find the probability that a cup of coffee purchase will be between 7.5 and 7.8. I know there's a lot of numbers, so let's label. So this is x1, this is x2. Those are part of the question. This is going to be A and B. So we are going to write down our probability as with random variable notation. 7.5 less than or equal, x less than or equal 8.2. So in this case, x2 minus x1, which is 7.8 minus 7.5 divided by b minus a, which is 8.2 minus 7.4. Using our calculator, we should get for this 0.375. So that is the probability that the next cup would be between 7.5 and 7.8. What is the picture for this? Well, suppose we have this graph that represents the distribution, in which the lowest is 7.4 and the largest is 8.2. Okay, notice this is going to look like a rectangular region because the probabilities will be the same for every single random variable. So they're asking us to find the probability that the next cup of coffee is between 7.5 and 7.8 milliliters. I mean, not milliliters, it's ounces in this case. So they're asking us for that area under the curve, which is basically 37.5%. Of course, my picture is not perfect, but that's no pun intended. That's the bigger picture of what it is. Okay. Find the probability that the next cup of coffee purchased will contain between 7.6 and 8.0. So this 8.0 ounces. In this case, well, so this will be x1 and x2. The probability that we get between 7.6 and 8 ounces, it's going to be 8 minus 7.6 over, what was it again? It was 8.2 minus 7.4. Using the calculator for this, you should get 0.5, which is basically, not percent, 0.5 is the probability. That's basically 50%. So it is 50% likely that a cup of coffee would be between 7.6 ounces and 8 ounces. Okay, let's look at another example. So let's say the probability that the next cup of coffee will contain more than 7.6 ounces. Well, in this case, it would be a good idea to draw a picture for this. Okay, so okay. So again, our parameters are 7.4 and 8.2. So this will be our region. And in this case, they're asking us to find the probability that the next cup of coffee will contain more than 7.6. So this is our 7.6 here. But more than 7.6 will be all the way basically between 7.6, that was a funny 6, between 7.6 and 8.2. Okay, so in this case, one of the givens is actually one of the questions. So this is going to be x1, this will be b, and as well as x2. So the probability that we get hold on a second. The probability that we get between 7.6 and 8.2 ounces will be 8.2 minus 7.6 divided by 8.2 minus 7.4, which in this case, I'm going to need my calculator because it looks like I lost that page where I have that information right here. All right, so this will be, so 8.2 minus 7.6 that's 0.6, and 8.2 minus 7 minus 7.4, and 0.8. So this reduces to 0.75, which is actually the 75%. Look at the portion of the graph that we plotted, actually, that represent that big amount, 75%. Okay, all right, so now let's move on to the central limit theorem. So the central limit theorem is an extension of the normal distribution, in which all we are going to do is change the standard deviation when we calculate the probability for a certain situation. So what's the idea? Okay, so every time we collect a sample that it gets larger and larger and larger, we find out that the distribution gets very close to a normal distribution. Okay, regardless of how distributed the population gets sampled. Okay, so now the thing is, so what are the restrictions in order to use the central limit theorem? Well, the number one restriction here is that the sample that we take is larger than 30 elements, or 30 or more. Okay, so, and in the other case, in the case that we know for sure that the population is normally distributed itself, the sampling distribution, the mean, it's going to be normal, and we don't need to be taking exactly a sample of 30. Could be 15, could be 5 even, because we know that the distribution is normal for the population. But if we don't know, well, then we need to take a sample of at least 30 or more. Okay, so so what happens? So what's the idea? As the sample increases, the standard deviation decreases, because this gets closer to normal. So when we take large samples, the data within elements won't have too much variation. So what happens? How can we translate this into formulas? Well, sample size increases, standard deviation of the sample decreases. So notice in this case, the standard deviation in this case will be divided by the square root of, and where do we get that from? Well, it's not within the scope of this course. Let's just use it. Okay, so let's look at an example. Assume that the average weight of an NFL player is 245.7 pounds with a standard deviation of 34.5 pounds. Okay, so this is going to be our mean and our standard deviation. Okay, in this case, we are going to look for the probability that the average weight of a sample is less than 234. Not just one player, or like one car, like we did in the normal distribution. In this case, we are taking a sample. We are finding the probability that not just one, but actually multiple elements in the sample. In this case, 32 or more, if we are not certain that the population is normally distributed, or any sample size if we know for sure that that the population is normally distributed. In this case, well, In the problem, they're not telling us anything about the population. The entire population of NFL players are normally distributed. However, that doesn't matter because in this case, we are taking a sample of larger than 32, or than 30, in this case, 32. So how are we going to calculate this? Okay, so find the probability that the average weight will be less than 34 pounds. Okay, let's denote this using random variable notation. So x is less than 234. Okay, so in this case, we're going to use Normalcdf, the same distribution, the same function, Normalcdf. So in this case, well, less than 234. Okay, let's do a little picture here. So if the mean is 245.7 and the standard deviation is 34.5. Okay, they're asking us for someone less than 234, which is below. So in this case, we are finding this area to the left. So we are going to look for a negative huge number, which is our lowest, and then the largest, which is 234, or the upper rather, that's lower, upper. The mean remains the same, 245.7. Okay, 245.7. However, the standard deviation is the one that changes, so it will be 34.5, but it's divided by the square root of the sample size, which is 32. Notice I highlighted that here with green. I'm going to highlight it here as well, so you see the connection. Okay, so this will be equal to, okay, let's put this on the graphing calculator. So let's clear second dist Normalcdf, and the lower it's a negative huge, upper, what was it, 234, 230, and the mean was 245.7, and the standard deviation, which is 32, wait a minute, not 32, that's oh, come on, 34.5 over square root of 32. 34.5 divided by the square root of 32, and close parentheses here, and go one down with the arrow and paste. That's going to give us 0.0275. Okay, that's basically 2.7%. If a random sample of same 32 NFL players is selected, what is the probability that weight of the sample is between 248 and 254? Okay, so we're going to do probability that we get 248 x 254. So that is normal CDF of 248, that's the lower, the upper 254, and then the mean and the standard deviation same as before, so 245.7 comma 34.5 divided by square root of 32. Okay, so let's put that on the graphing calculator to find that probability. Okay, so let me clear and clear. Second this Normalcdf. Good news, some of the parameters are safe. Our job is just to change the first two, 248 to 54. 248 to 54, and just scroll down all the way to paste. And 0.2663. 0.2663 is the probability, basically 27% if you will, rounding. Okay. A random sample of 32 NFL players is selected. What is the probability that the average weight of the sample is between 242 and 251? So basically the same. Let me actually copy. It's going to be very similar calculation. Okay. So let me erase the first two numbers. And this will be 242 and 251. 242 and 251. Okay, let me go to the calculator. Clear, second list, Normalcdf, same parameters except the weights, which are 242, 251, 242, 251, scroll down 3, click enter on paste, and do the calculation. All right, so we get 0.5356. That's our probability. Okay, so now let's make a little change. So for letter D, we are going to have the exact same parameters, the exact same lower and upper. But in this case, we are not going to take a sample of 32 players. Okay, in this case, we are going to take a sample of, okay, let's see what happened here. Okay. Give me a second here. So in this case, we are going to take a sample of 120 players. So, not 32, so let me change that 32 and replace it with 120. And see what happens when we increase the sample size. So let me go to the calculator. I'm just going to go up here and click enter to copy the numbers. So I'm going to have 120 players and click enter. I get 0.8338. Okay, let's compare and discuss about this. So let's compare the probability when we have just 32 players and 120 players, and let's see what happens. So notice in this case we're taking a sample size from, because the population is big enough, so because our sample is larger, so the probability would be more likely to find someone that is between 242, that weight to between 242 pounds and 251. So that's what happens when we increase the sample size. That likelihood is increasing because you have a lot more people to choose from, a lot more elements in your sample to choose from. Okay, so that'll be for letter E, the comparison between the two parts C and D. And this is the end of this chapter, chapter 6 on continuous probability distribution. See you on the next video. Okay.